Hello everyone, we are group 4 members and I am Jasleen Kaur and my teammates are.
Mohammad Ezdani Sheikh.
I'm Giyas Nizamuddin Sheikh.
So our presentation today focusing on the search paper topic named 2DFQ, two-dimensional fair queuing for multi-tenant cloud services. And these are the authors of our research paper. Next slide. So here is the motivation behind this. So why fine grain isolation matters. So this slides sets the foundation for the problem statement in cloud services like storage system, example HDFS, databases, queuing systems. Multiple tenants share the same processes, while this sharing enhances cost efficiently and scalability. It also creates contention within the process for CPU time, input, output, and system logs. If one tenant becomes resource aggressive, it can overload the sharing component like HDFS name node, causing other tenants to starve. In the worst case scenario, single tenant causes a denial of service or cascading system outage. This shows that the fine grained scheduling is not just performance optimization, it's essentially for the system reliability. So the next is real world denial of service examples. To emphasize the practical importance of the problem, the authors provide examples for the production systems. In eBay's Hadoop clusters, aggressive API users cause denial of service attacks on the HDFS name node. In the some of the clusters, background tasks are poorly designed. MapReduce jobs flooded the metadata serves and again causing failures. Impala queries failed in Kudu clusters due to the lack of proper resource sharing. In cloud stack, aggressive use of shared control plane by some users caused management server crashes. These are not isolated events. They highlighted the multiple tenant isolation problems affect real world production grade systems, making this a high priority, practically problem to solve. So the next slide. Ad hoc isolation is not enough. This slide critiques existing solutions, which the authors call ad hoc, like setting manual thresholds using coarse grain rate limiting or hard-coded caps. For example, HDFS has static priority queues, Cloud Stack applies manual rate bounds. However, these mechanisms don't adapt when workload changes. They require constant manual tuning, and worst of all, they don't solve the root cause, unfair scheduling within a shared device. The research community and practitioners alike frequently refer to multi-tenant isolations as a hard, unsolved problem, and this paper builds its motivation on that gap. Next slide. Fair queuing. So this like transitions into the related work algorithm like weighted fair queuing, WFQ and WF square queue are well established for the network traffic. They work by creating a per tenant queues and tagging each request with the virtual start and finish times for the scheduling. But cloud services are different from network traffic here. Request cost can differ by four or more orders of magnitude. A small metadata fetch may take milliseconds, while a dataset load may take seconds. If a scheduler underestimates a large request cost, it gets placed ahead of others, leading to head of line blocking and degraded latency for everyone. So while WFQ works in theory, it fails in practice under variable, unpredictable request loads. Next slide. So what a good scheduler needs. The author argued that a good scheduler for the cloud services must meet four critical properties: work conserving, no thread should be idle when there is a pending work, non-bursty, fairness, don't let one tenant dominate all threads for the longer duration, lightweight and application layer deployable, It should require no kernel or hypervisor changes, dynamic and adaptive. It must adapt to unknown or shifting workloads. In essence, they want a scheduler that's smart, reactive, and efficient even in unpredictable and high concurrency environments, which is where 2DFQ comes in. Next slide. This is the design overview. Here, the paper introduces the core idea behind 2DFQ, a new scheduling strategy that tackles both known and unknown request cost using two dimensions, request separations and pessimistic cost estimations. Staggered eligibility in threads become eligible to at offset times favorably small, lightweight jobs on high index threads and deferring large jobs to low index threads. The workflow is robust because there is a request which are queued per tenant and assigned a virtual clock. Costs are estimated and pessimistically inflated for unknowns. Schedulers select eligible requests based on the virtual time order. Resource usage is tracked and virtual times are corrected retroactively. This pipeline leads to better performance, low latency, and consistency performance even for many tenants. Next slide. So here is the introduction. This slide reiterates and formalizes the concept. 2DFQ brings fairness across two dimension times and threads, time dimensions and thread dimensions. Dimension ensure tenants get consistent across overtime and avoiding starvation. Thread dimension ensures that big requests don't hog all the threads, isolating their impact. This method reduces the bustiness when large request blocks and the system and improve the latency stability for small frequent operations. In essence, it gives each tenant a fair share both over time and across the computer resources. Next slide. So here are the key design principles. The authors establish four design goals that drive the 2DFQ architecture. Fairness over time and threads. It's not enough to be fair over the time thread level. Isolation is needed to protect small tasks. Reducing tenant inference by routing large jobs to separate thread. 2DFQ prevent aggressive tenants from degrading system-wide performance. Adaptability to workload changes. The scheduler monitors request behavior in the real time and adjusts scheduling strategies dynamically. Stable and service rates. Even during workload spikes or tenant bursts, 2DFQ ensures service rates remain consistent, which is a vital for SLAs in cloud systems. So next is continued by Muhammad.
Uh,
Muslim.
Here comes the challenges in existing schedulers. Uh, uh, the main challenges are irregular scheduling patterns. Like the scheduling algorithms WFQ and WF2Q produce irregular service delivery because they create periods of intense utilization with subsequent extended waiting time for users. And larger request traffic that controls all processor threads pushes away the execution of smaller requests, which causes user delays to extents. Um, After the another challenge is the wide range of request costs. The enormous range of request sizes spanning multiple orders in cloud environments creates difficulties for previous scheduling systems to achieve efficient management. The time needed to execute a metadata fetch operation amounts of 2 milliseconds, but large data set retrieval requires seconds. Yeah, in the picture we can see that tenants with small requests are affected and the burstiness is proportional to size of large requests. Like for the size one, it is a normal, but while coming to the large sizes, the proportionality goes more. And the next slide is a few more challenges that are existing in these schedulers are unpredictable request costs. Cloud workloads create unpredictability in cost because elements like cache status or input output demand continuously changing in the input output demands. Such unknown variables cause difficulties for order scheduling system, resulting in proportional suboptimal resources usage and reduced efficiencies. And another challenge is scalability challenges in high concurrency. Like several tenant system simultaneous requests operate using problems, but it gives the interference problems. WFQ and WF2Q fail to deliver effective performance management at such high levels of concurrent execution. And while coming to two-dimensional scheduling, a fair allocation over time. During the period, all tenants will obtain their proper allocation of system resources. Through this methodology, resource deprivation issues are prevented, which allows continuous access at maximum usage rates. Size-based thread allocation. The system distributes requests to threads based on size, with big requests intended for threads and smaller requests assigned to different ones. The method prevents large request operations from monopolizing the all system threads, which would negatively impact smaller request execution times. And another one is offset scheduling, which is staggered timing. Every thread possesses its own schedule for request eligibility periods. Smaller requests begin their execution process more rapidly on selected threads, while maintaining delay time for larger requests, which enhances minimum wait periods for smaller tasks. Better handling of high concurrency. 2DFQ 2DFQ distributes program execution demands equally between different time intervals, while managing simultaneous requests from varied threads, so the system can process numerous requests efficiently. And handling unknown costs. Efficient thread usage. The system directs requests to threads depending on their own unknown cost to maximize system resources usage. Define the thread combination using high index value, serve quick processing of smaller duties. The thread system routes longer operations to lower index threads, because this action shields them from interfering with the smaller or faster tasks. Stable performance for predictable users. The system provides dependable performance for users who carry out repetitive tasks on schedule. The system provides users for who spend frequent small metadata requires with consistent low response times, like reliable service levels. The separation of small requests under the 2DFQ protocol maintains stable service quality by minimizing disruptions which occur from bigger and variable sized requests. And handling unknown costs. Handling unpredictable requests. Scheduling becomes disrupted when requests present uncertain resource requirements, especially through underestimating their demands. The seemingly minor request may require a lot of system resources, thus preventing other operational using a conservative most expensive cost estimation for unfamiliar requests to stop them from monopolizing thread allocations. Maintain steady performance for anticipated workloads becomes possible through this delay of unpredictable requests, even though their execution time increases marginally. Adaptive scheduling via feedback. Each completed request goes into the system for cost tracking before the database uses it to create improved budget projections. The continuous learning process improves the scheduling precision throughout its operations. And here comes the pessimistic cost estimation. As we can see the box plots over in this picture, from here we can understand that monitoring peak request costs, favoring predictable workloads, avoiding scheduling spikes, Coming to monitoring peak request workload costs, request costs, the system stores maximum observed request costs from tenants and APIs to use as reference when processing unfamiliar requests. System resources stay protected from excessive stress by adopting this defensive measurement practice. Uh, and another one is favoring predictable workloads. A system design puts low cost, steady tenancy requests first to reduce operational delays that occurs when serving unpredictable users, avoiding scheduling spikes. A built-in feature increases system reliability by setting unspecified request costs higher than actual but without affecting predictable client demands. And this picture shows the distribution of cost distribution of 10 APIs, which is and the cost distribution of 12 tenants. And measurements of Azure storage show widely varying request costs. Whiskers extend to first and the 99th percentiles, while violins uh, show distribution shape and mitigating impact of unknown costs. In this, we have two categories like adjustments after completion and maintaining fairness over time. While coming to adjustments after completion, when a request ends, the scheduler evaluates the when request ends and the scheduler evaluates the comparison between estimated and actual resource consumption. The scheduler implements an update a process for virtual time, which considers this resource usage difference. Coming to maintaining fairness over time, the session duration determines whether the tenant gets a credit or extra charges demanding a on actual versus estimated resource usage. The method secures fair resource distribution to tenants throughout system operations. Here are the box plot and the uh, graph for the tenant versus cost and the mean request size versus coefficient of variation. Another, while coming to real time cost adjustments, regular resource checks, system monitoring resource usage for extensive requests occurs on a periodic basis to verify actual costs, match predictions, uh, and early detection of both overused and underused resources takes place as a result, which shortens the feedback delays. And coming to enhanced precision, the another real-time cost adjustments is enhances precision. Faster action plans to address resource usage issues can be taken when resource heavy requests are identified right away, thus preventing long delays of thread operations. And another one is efficiency and accuracy trade off. The monitoring system strikes a balance between keeping expenses low and generating exact scheduling decisions. And here are the best scheduled overview and the smooth schedule overview. Here we can see the distribution of classes regard while with the schedules. And coming to implementation, the core components are request queue manager, thread pool manager, scheduling strategy. While coming to request queue manager, the system operates distinct queues containing logical requests for each existing tenant, tracks virtual time for fairness. The system determines when applicant requests become ready to undergo processing steps. Thread pool while coming to thread pool manager, the thread distribution process depends on an evaluation of request costing estimates. The thread pool manager oversees the operational threads while scheduling over worker units. The scheduling logic execution takes place through dispatching tasks by using the essential algorithms. Scheduling strategy. Adjustment eligibility formula is given as SRJ minus I by N into LJ. The system tracks separate virtual time periods for each operating thread And the system uses request cost distribution to avoid network congestion. Every thread receives active work assignments, work conversation, work conservations whenever it is possible. And while coming to other implementations like resource management, tracking, and adjustment mechanisms. Well, coming to resource management, there are two separate categories like estimating, two separate tasks like estimating costs and the ensuring fairness. While coming to estimating costs, the system used a conservative approach for estimating request costs at their highest possible value. The system tracks and also the system tracks historical cost data through both tenant based and the API based segments. And also it it conducts ongoing actual usage tracking while programs run. And also it collects the usage data which serves as input for making better future cost predictions. And coming to ensuring fairness, the system checks service delays that customers experience at the tenant level. And also it modifies virtual time periods from when disparities between tenants appear when disparities between tenants appears. And also it performs fair resource distribution during time periods through compensational procedures. Well, coming to tracking and adjustment mechanisms, there are two types of it is distributed in two categories like retroactive adjustments and ongoing usage updates like refreshed charging. While coming to retroactive adjustments, the system records actual resource utilization once a task finishes. The system tracks and adjusts costs that differ between original projection and final execution expenses. And also it refreshes virtual time measurement to match actual resource usage. While coming to ongoing usage updates, refresh charging, like it is periodically checks long running requests, and also it applies early corrections to if needed. And also it remains updated about the current resource usage levels. And the next is here comes the system architecture. uh, this system architecture is going to explain by Gias.
Yeah. Hi. Now I'm going to go through you from system architecture. So it has mainly thread polling, interaction, request queue, and scheduling logic, feedback, and cost adjustment. So in thread polling integration, uh, like we run it, it's operationally straight for the thread polling frame, which regularly appears in the multi-tenant solutions. And the scheduling procedure act, uh, access the workers thread, specifically thread to maintain equal workload distribution across the entire system. See, now in the request queue, single logic queue exists for each tenant's entire, so they can receive incoming requests. In the schedule logicking, the active scheduling system continuously monitor unusual threads while it picks valid request present in the tenant queue. In the each thread performs eligible checks one after the another, two different times to achieve equable and unconditional request distribution. Like in the image, we see multi-threading, mm, uh, uh, multi-threading how have been accessed between the five persons here, like five tenants and their requests. Now coming to the feedbacks, the real-time feedback system dynamically refer cost estimated and relocating for periodic refresh cost methods exist to like tenants billing to the system usual reality. Next, please. Now coming to key algorithm, like the red lines request in the run occurrence at unique time, which depends on the thread. The system implements a modified computing methods. Uh, And the scheduling rule provides highly prioritized to small tasks on the threads which have high index values. The scheduling request in the system selects the request which will reach complications at the first time. And we see the expression of the computation time which is shown in the slide. Next, please. And the post execution adjustment after each after each process finished, the system checks how actual resources matches the previous estimates, and the extra load causes the tenants to give additional time adjustment. And it is like ongoing unusual real time cost estimates updates occurs at a regular maintenance interval in the system as it monitors ongoing requests. The system utilizes its methods to stop outgoing estimates for processing delays in the system operations. Next. Now coming to evaluations. What we have evaluated from the given article, like we know that the request cost, which with the system know the cost of each request ahead of time. It is evaluated for its capacity to offer consistency and fair service at all tenants, even when some requests are much more expensive than others. Like we have seen previously, some requests mm, which are much higher than the previous. We have come to a conclusion. The unknown, coming to the unknown request. In some circumstances, which request fee or uncertain, the extended schedule is equivalent for its capacity to provide some service, especially for predictable tenants. Now coming to robotness, like the coming to like the environment determines whether two dimension can isolate the impact of unexpected tenants gradually that this vary to do some damages which is received by one or another. Next, please. Now here we have some evaluation steps integrated in the graph. Here we can test two dimensionals and baseline schedule in the disaster event simulus with the systematic workflow using st- Azure storage traces. Other algorithms, including SFQ and DRR, which were not included in the final review due to this practicable indeed finds to WFO and WF square Q. In the graph, we have shown how it goes on. Uh, now, now the comparison forces on WFQ and WF square Q, which other variable did not show significant difference in fairness or performance under testing settings. Next, please. Service quality improvements with 2DF and 2DFQE. The review evaluated both equally and effectiveness by measuring multiple performance parameters such as service tags, service lag variables, service rate latency, and the Gini index. In the graph, we can see the number of expensive tenants and the service lags. Now, when request fees are unknown, 2DFE reduces service lags variations and decreases style latencies and predictable tenants by up to 100%. We can improve it by 99% latency by up to 24x in equal world workload settings. Next, please. Now, here we came to a conclusion that the 2DF provides a robust solution for fair scheduling in multi-tenant cloud system by combining fairness across time and threads. The algorithm significantly reduce latency and improve the reliability of service for predicting workflow, makes it suitable for more cloud environment. In this paper, the author have clearly explained how it uh, like how the workflow goes through, and practiced framework for specifically consistency, and they successfully defined and implemented and evaluated such work frames. We can say that the paper have been well balanced, uh, with its background and motivations are clear, and the case study are well explained in it. Yes, we have learned many things from this paper, and we have implemented many things, like how to apply formal verification tool to real world protocol with equivalent or relaxed consistency. So that's all we want to present to you. Thank you very much.